Okay, yeah, thank you for attending the class today. Our today topics is still the free vibration, continue from last time lecture. But last time our free vibration didn't have the damping component in the system. So it's a kind of simple harmonic vibration, just only the spring and mass. But in this class today, it is a more specific case of free vibration that has the damper in the system. So the behavior of the system will be damped. I mean, the response of the system will be under the effect of the viscous damper. If you could remember, we talked about the standard form of the second order system and show the root of the second order equation on the complex plane. And that root is related to the different type of response. If the root is on the real plane, the response has no vibration. If the root is on the left-hand side of the imaginary plane, if you remember, if the root is on the real, we have the imaginary part of the root and the real part of the root. If the root is on the real axis, the root has no vibration. And if it's on the left side of the imaginary axis, the response converge. If it's on the right hand side, sometimes it's diverse. And if the root has the imaginary part as a complex conjugate, we can see the vibration of the root. And if the root has only the imaginary part and the real part is zero, it will vibrate with a constant magnitude as a simple harmonic vibration. And yeah, we also talk about auxiliary equation, that we can find the root of this and we can categorize the type of the vibration of the free vibration. And today we will review these two topics, but we won't spend much time on this. And the new things, the new, how to say, the new variable that we're gonna use to separate the type of the free vibration is the critical damping coefficient. We will learn in detail what is this variable and what is the value of this variable that we can say that the vibration is underdamped, is critically damped, or overdamped. Today we will go into the detail of the critical damping coefficient and the three types of the free vibration under the effect of the viscous damping. And as I mentioned in the early of the class, that in this class we will give an introduction to you about using the MATLAB. So today you will learn how to solve the response of the vibration by the analytical method. And then you will learn how to plot the result of the analytical solution by the MATLAB program. In addition, to validate your analytical solution, you derive the analytical solution and you plot it by the MATLAB. Today, I will teach you an alternative way to obtain the solution of the differential equation, and you also can plot it, and you can compare these two plots. The first plot, you solve the equation to obtain the xt, or the displacement varying against the time, and you plot it. And the second method, you didn't solve the equation, but you write some code on the MATLAB, and the MATLAB solve the equation for you, and you plot it, and you can compare. So by these tools, you can learn it by yourself. I mean, after the class, you can put different type of initial condition, different type of mass, spring, and damper value, and also the different initial condition x0 and v0. You can put different value of this and try to analyze the response xt for the given value of this, and it will be result in the 3 different type of this, and you also obtain xt, and you can plot it on the MATLAB. And in order to know that, in order to know whether your obtained solution is correct or not, you have an alternative method here, and you can compare the plot. So yeah, with the thing I'm gonna teach you today, you can have tools to practice by yourself with how to say, extended example. And the logarithmic decrement. The logarithmic decrement. Wait a second. I couldn't see attendee screen. You still can hear me, right? Everyone still in the class?
Yes.
Okay, thank you. I didn't see your face, so I just worry that the connection has problem. Okay, the logarithmic decrement. The vibration sometimes decrease the magnitude as the effect of the damper. So this parameter can tell us how fast the magnitude of the vibration decrease. So if the vibration decrease the magnitude with high rate, it means that our damper has high value. So it has some relationship between the damping coefficient and also the damping ratio to the rate of change of the magnitude of the vibration. So This will be in the topics of the logarithmic decrement. Because in the real system, we can measure the mass component, and also we can measure the stiffness of the spring. We may sometimes can obtain the stiffness of the spring by the static deflection, but the C parameter or the damping coefficient is not easy to obtain in the real system. So by applying the concept of the logarithmic decrement, we can find a way to obtain the damping coefficient from the measurable data of the experiment. And today we will provide some example. The measurement examples means the example that relate to the measurement in the vibration system. And also some examples are about the design. So it means how can we design the component in the vibration system so that we can get the design response. So today example consists of two types of example. And yeah, at the end of the class, we will see the code of the MATLAB that we can compare the plot of the response. Okay, to review the standard form of the second order system. Actually, for this slide, we already talked in the previous class, so nothing new, just review. We have the second order differential equation of the free vibration system. The force here, external force, is equal to 0. So from last week, if you could remember, we did something like here. We transform the equation by divided by mass, and we transform it to the standard form of the second order system. In the standard form means in the terms of the damping ratio and the natural frequency. And if you could remember, for the second order equation, the solution to the equation can be assumed to be in the form of the exponential. We have one constant multiplied by the exponential function of the root multiplied by the time. So by assume the root of the equation to be in this form, if we take the second derivative and the first derivative of the x, we can obtain this. If we do the second derivative, we're gonna have the alpha square. And yeah, I should do it one more time. If we take the second derivative of this solution, what we're gonna have is we're gonna have the alpha square. So we will have a alpha square e power alpha t. And if we do the first derivative, what we're gonna have is we have a and alpha and e power alpha t. And for the zero time derivative, we still have the same one, nothing changed. So yeah, by combine the common term, what we have is plus 2 sine omega n alpha plus omega n square and e power alpha t equal to 0. And we know that the constant a or the exponential term not gonna be 0. To obtain the root of this equation, the terms in the parentheses should be 0. So the root should equal to the quadratic root is written in this form. Or we can write it as and last week we said that this can be called as a damped natural frequency. And if you still remember, on the complex plane, we have the imaginary part of the root and the real part of the root. And the real part is here, minus sine omega n, and the imaginary part is here, omega n square root 1 minus sine square, square root of the sine square. And yeah, by this, if the value of the damping ratio is 0, if the value of the damping ratio of is 0, it means that the root will be plotted on the imaginary axis, and the root will equal to plus and minus j omega n. And in this case, the vibration will be just a simple harmonic, or the case of vibration will be undamped. But if the value of the damping ratio is between 0 and 1, the value of the root will have the real part minus sine omega n, and the imaginary part, and in this case the damping ratio is between 0 and 1. The response that correspond to this type of root we call underdamped free vibration. And if the damping ratio is equal to 1, inside the square root will be 0, and the root will have only a real part. In this case, we call critically damped free vibration. And the final case is when the damping ratio is more than 1. when the damping ratio is more than 1, inside the square root will less than 0. So we're gonna write it in a new form. If the damping ratio is more than 1, we're gonna write it like omega n square root psi square minus 1 instead. And in this case, the damp is more than 1. The damping ratio is more than 1. So we call overdamped, which means the damping ratio is too high in the system, and it makes the system like slow. Today, we will go into the detail of these 3 types of the system, because for the first one, we already talked in the last class. And yeah, you should know the relationship between the damping ratio and the parameter of your system. You know that the omega n is related to the spring constant and the mass. And you also know that these 2 terms should be equal. So C divided by M is equal to 2 psi omega n. So the damping ratio is equal to C divided by 2M omega n. And omega n is the square root K divided by M. So you can relate the damping ratio by the damping coefficient, the spring stiffness, and the mass. Okay. And the second way to categorize the type of the free vibration is to use the auxiliary equation. So the second order system with the equation of motion of mx dot dot plus cx dot plus kx equal to 0. The auxiliary equation is to use the variable r to represent the derivative of the x variable. So what we need to do is to solve this equation. So to solve this equation, the quadratic root r equal to minus c plus and minus square root c square subtract by 4mk divided by 2m. So the terms inside the square root has meaning. If the c square minus 4mk is more than 0, if this term is more than 0, it means that the square root term will be a real number, and the root of the equation will be a distinct root, a different real root, R1 and R2. R1 and R2 will equal to this. R1, we're gonna use the plus, R2, we're gonna use the minus. So in this case, Yeah, if the root has two real roots, it's gonna be a kind of overdamped system. So in this case, it's related to overdamped system. And if this term is equal to 0, what we can obtain from this, if this term is equal to 0, we're gonna have a repeated root, which means R1 equal to R2 and just equal to R equal to minus C divided by 2M. So in this case, we call critically damped system. And if the terms C squared subtract by 4mk is less than 0, we're gonna have two complex roots, which are the complex conjugate. The R1 and R2 will equal to minus C plus and minus the imaginary number multiplied by 4mk subtract by C squared. And we're gonna have a complex conjugate root. Yeah, the complex conjugate root here is underdamped free vibration. Yeah, please don't confuse between underdamped free vibration and undamped free vibration. Undamped free vibration, the real part is 0, and we just have the simple harmonic vibration, no damper in the system. But if we have damper in the system, we're gonna have the damping ratio. But if the damping ratio is between 0 and 1, the type of the vibration is underdamped free vibration. We have damp, but the damp is between 0 and 1. So today we will see how is the response of these three types of different types of system. But before going on that, we're gonna see these terms. We can see that the term C squared subtract by 4mk is important. It can tell us the system gonna be overdamped, critically damped, or underdamped. We have a parameter called critical damping coefficient. The term C squared subtract by 4mk equal to 0. With this, the C that make this equation become true is the C critical or critical damping coefficient. So the critical damping coefficient is equal to square root 4mk or 2 square root km. The damping ratio The damping ratio is the ratio between the damping coefficient and the critical damping coefficient, or the damping coefficient divided by 2 square root km. Yeah, critical damping coefficient. The critical damping coefficient is the damping coefficient that make the system become critically damped vibration. And the damping ratio of the standard second order system is the ratio between the damping coefficient and the critical damping coefficient. So the ratio is equal to C divided by 2 square root km. Yeah, if you remember in the last slide, we also derived the damping ratio through the standard form of the second order equation, and it equal to C divided by 2 square root km. So it's the same. Yeah, and critical damping coefficient is this one. So in this slide is nothing. And underdamped free vibration. What is the underdamped free vibration? The root of the second order equation is equal to minus sin omega n plus and minus imaginary part of the damped natural frequency. The underdamped vibration, the damping ratio is between 0 and 1. And the root is this form, has the real part and the imaginary part. We know that for the second order system, we can write down the solution of the second order system in the terms of the linear combination. The linear combination of the exponential of the root okay, to make it become the same notation, I should write down, it's like here. The response or the displacement as a function of time can be written in the terms of the linear combination of two exponential functions. And the exponential will have the power of the first root and the second root. The first root has the plus and the second root has the minus. So the response is equal to the first root will be minus psi omega n and plus j omega n square root 1 minus psi square t. And the second part will be a2 multiplied by e power psi omega n and minus j omega n square root 1 subtract by psi square t. But by the Euler identity, in the last class we try to transform the complicated solution in a more simple form. We said that xt of the complex conjugate root can be written by 1 amplitude multiplied by the real part and psi function of the damping, the damp natural frequency and a phase angle phi. So for the case of the undamped free vibration, the solution can be written into this form. The damping ratio, we know. If the system, we know mass, we know the stiffness of the spring, and the damping coefficient of the damper, we can compute the damping ratio, the natural frequency, and also the damp natural frequency. The damp natural frequency is equal to the natural frequency multiplied by the square root of 1 subtract by psi square. So every time the damp natural frequency always less than the natural frequency, the undamped natural frequency, because in this term always less than 1. So if the system don't have the damper, the vibration can go faster. The omega n is high, and the amplitude always constant, never change. But with the effect of the damper, and the damping ratio is between 0 and 1. The response will come into this type. The magnitude is decay by the exponential. The magnitude is decay by the exponential. And the psi function, instead of having the natural frequency omega n, it will have the damped natural frequency that always lower than the undamped natural frequency. So in this equation, if we know M, C, and K, we know the damping ratio, we know the natural frequency, and we know the damped natural frequency. But we still have two unknowns. We don't know the magnitude, and we don't know the phi. So these two parameters can be obtained from the initial condition of the problem. at least we should have two initial conditions to solve in order that we can obtain A and C. Most of the problem, we can obtain the initial condition when time equal to 0, which means we're gonna know the displacement when the time equal to 0. And we're gonna know the velocity or the first derivative of the displacement when time equal to 0. So if we know two of these, how can we solve for A and the phase shift? So from this, can we find the first derivative of this solution? If x equal to this, if we find a first derivative for x dot t, there are two parts. The xt is a product of two parts. So we should find, if you remember, d by dt of the product of the two parts is equal to A d by dt of B plus d by dt of A multiplied by B. So we have two parts here. So x dot t is equal to minus A. Okay, is equal to A minus sine omega n e power minus sine omega n t. And the second term, sine omega d t plus c. This is the first term here. For the second terms, the first term still be the same, but the derivative of sine function will be cosine. And if we find the derivative of omega dt by dt, we're gonna have the omega d. So yeah, finally, the derivative of the solution can be written as a combination of these two terms. So if we say x at time equal to 0, x0 is x at t equal to 0. So we're gonna check this equation and we're gonna have x0, or the first initial condition, is equal to what's gonna happen when the time t equal to 0. The exponential will be the exponential of power 0, which is equal to 1. So if t equal to 0, the exponential term will equal to 1. So we will have only a sine. And also t equal to 0, omega dt also 0. So we have only a sine phi equal to the first initial condition, x0. How about the x dot t when t equal to 0? X dot t when t equal to 0 when t equal to 0, the exponential term here, t is 0. So exponential terms also equal to 1. So the V0 will equal to A, okay, minus A sine omega n, and t here equal to 0. So we will have only sine of phi. And for the second term, yeah, when t equal to 0, the exponential term equal to 1. So we're gonna have A omega d cosine and t equal to 0. Like here. So yeah, what we can see here is how can we solve for the A and the phi for a given value of x0 and v0. Now we have equation 1 and equation 2. So in order to solve these two equations, yeah, what should we do? I recommend we write in this equation in the terms of cosine of phi. So for this, what we have is the cosine of phi is equal to V0 plus A sine omega n, but A sine phi is equal to x0. So can you see this? X0 is equal to A sine phi. So if we move this to the left-hand side, we're gonna have V0 plus sine omega n multiplied by x0 and divide by A omega d. A omega d. This is the cosine of phi angle. The sine of phi angle is equal to x0 divided by A. So now we have sine and cosine of the phi angle. So in order to obtain the phi angle, the phi is equal to the arctan of the sine divided by cosine. So yeah, now you know how can we obtain A and phi for a given value of MCK. And if once we know the phi angle, we also can obtain A by this relationship because we already know the initial condition x0. So yeah, this is just only the concept. If you still not clear in this slide, don't worry. We're gonna have the example that show you how can we obtain the A amplitude and the phi or the phase shift for a given value of MCK and initial condition. Okay. Part1, you didn't see this one, right? Okay, I'm gonna repeat this one again. Maybe this I write it not clear. So we're gonna move it to here. Sorry, it's too messy on this slide. So the cosine of phi is equal to V0 plus psi omega n x0 divided by A multiplied by the damped natural frequency square. Is that correct? Let me check. It comes from, oh, no, I'm sorry. I also confused with what I write. Yeah, it's just this one. So the cosine of phi equal to V0 plus psi omega n x0 and divide by A omega d is this one. Yes. Anybody still have oh no. Part1, it's just A omega d. We don't have square. We just move this one to be the denominator. So it should be only A multiplied by the omega d, not square, not omega d square. Okay. All right. And this is the case of the underdamped free vibration. And the response will be the vibration with constant natural frequency. But natural frequency will be decreased from the undamped natural frequency to the damped natural frequency. But it has the constant omega d. But the magnitude will be decayed by the exponential terms. This is the undamped free vibration. How about the overdamped free vibration? The overdamped free vibration, if you remember, the root is equal to psi omega minus psi omega n plus and minus omega n and square root psi square subtract by 1. And for the overdamped, the damping ratio is more than 1. The damping ratio is more than 1. And we're gonna have 2 real root. So the same concept, the same idea with the previous case. Xt is the linear combination of 2 roots. So xt equal to a1 e power alpha 1 t plus a2 e power alpha 2 t. So it will equal to a1 e power minus psi omega n t and e power omega n square root psi square minus 1 plus a2 e power minus, I forgot t here, okay, psi omega n t and e power minus omega n square root psi square minus 1 t. Yeah, the common term in here is this term. So we can combine it like here. E power minus psi omega nt and multiply by a1 e power omega n square root psi square minus 1 t plus a2 e power minus omega n square root psi square minus 1 t. Okay, this is the case of the overdamped free vibration. So the damping ratio is more than 1. And in the square root term here is more than 1. So the root will be the distinct root, which means we have two real roots which have different value. And the response xt is the linear combination of these two roots, and we have the common terms here. We have the common terms, and these two terms which are different. So yeah, the damping ratio is the real value, and we can obtain the real value. And the total response is the linear combination of two exponential functions and has the decay here. So not as complicated as the previous case that we have the complex conjugate. So again, to solve the problem, we still need to know the initial condition. And we need to know the x0 and v0 in order that we can solve for the unknown a1 and a2. If we see in this plot, yeah, these three cases has the same value of m, c, and k, but they just have different initial condition. So what can we see from the initial condition? What is the physical meaning? In the first case, what can we see in the first case? The velocity at the origin time is 0, but we have initial displacement to the positive 0.3. And after that, the spring will pull the system. Yeah, the second order system has spring and mass and a viscous damping. We have M, C, and K. And in the first case, we just pull the mass maybe to the right hand side to the positive x0 and start from the rest. We release the system from x0 equal to 0.3. What happened to the system is the spring try to pull the mass back to the equilibrium. So the displacement will decrease to the equilibrium position. But if you can see, we don't have vibration in this case because the effect of the damping coefficient is dominant and the damping ratio is more than 1. The motion of the mass is very slow. The spring tries to pull the mass to the equilibrium, but the damper try to resist, try to generate the force on the opposite direction to the velocity, and the motion is slow under the effect of the spring force and the resistance from the damper. Yeah, in the case 3, also just the, how to say, the opposite motion to the first case. We begin with the original position from minus 0.3. So we may move it to the left-hand side and just release the mass, and the spring will kick the mass to the right-hand side to the equilibrium. And the damper C try to resist the motion. In the second case, it's different. In the second case, the initial position is 0, x0 equal to 0, but we have the velocity when time equal to 0, and the velocity is positive. So it means the displacement is increased. So the mass has the velocity to the right-hand side at time equal to 0. And it passed x equal to 0 when time equal to 0. And when it go to the right-hand side, yeah, the spring try to pull it back to the equilibrium. The damper, the force due to the damper, just go on the opposite direction to the velocity. So when the velocity, when the slope is positive, the velocity is to the right-hand side. The force from the damper is to resist the motion. So it will go to the downward or the left-hand side. But when the spring pull the block to the left-hand side with the velocity to the left-hand side, the damper resist the motion, so the force will be to the right-hand side. Yeah, if you remember, the force due to the damper is minus c x dot. The direction always on the opposite direction to the velocity. The velocity is the slope of the curve that you see here. This is the plot between the displacement and the time. So the velocity is the slope of the plot. The note to this is we have no vibration. Yeah, as I mentioned, we have no vibration, and we have high damping ratio in this case. And this one, be careful. We have no damp natural frequency. Be careful here. The damp natural frequency in the previous slide is equal to the undamped natural frequency multiplied by the square root 1, subtract by the square of the damping ratio. But in this case, the damping ratio is between 0 and 1. This is for the underdamped. For the overdamped, we don't have the damped natural frequency. Be careful. Okay. And the third case, is the critically damped. Critically damped means, if you remember, the root is equal to minus psi omega n plus minus j omega n square root 1 subtract the damping ratio square. But critically damped, the damping ratio is equal to 1. So the damping ratio is equal to 1. The alpha 1 and alpha 2 have the repeated value of minus omega n. So for the repeated root, if you remember, xt will equal to a1 plus a2t multiplied by e power omega n t. Yes, in this case, for the critically damped, for the repeated root, we have a1 plus a2 multiplied by t and multiplied by the exponential decay. And yeah, the damping ratio is equal to 1. So the solution is simple. But what we need to do, the task that we need to do is the same. We have the initial condition, which is the initial position and initial velocity. And we need to solve this in order that we can obtain A1 and A2. And if we see the response of the critically damped, if we compare with the overdamped, the critically damped, is the case that we have a smallest possible damping ratio for no vibration. Smallest possible damping ratio for no vibration is the definition of the critically damped. What if the damping ratio is slightly higher than 1? If the damping ratio is slightly higher than 1, yeah, it still have no vibration. And it will be the case of the overdamped. But if the damping ratio is less than 1, we will have vibration. And it will be the case of underdamped vibration. And one more note to the critically damped free vibration is, with this, the damping ratio will, how to say, is the damping ratio for the fastest return to 0. without vibration. If we have the damping ratio equal to 1, the response, the displacement will return to the 0. Fastest compared to when the damping ratio is more than 1. But it may slower than when the damping ratio is less than 1. But if the damping ratio is less than 1, although it goes faster, it's gonna have vibration. If you want to stop, if you want to, how to say, bring the displacement of the mass to the equilibrium as fast as possible without vibration, you should select the damping ratio to be the critically damped value. When we design suspension for the car, for a car, yeah, we may prefer the damping ratio to be the critically damped value. I mean, to become 1. But we need to consider when the mass of the vehicle change, the factory may design the damper so that, okay, if you remember, the damping ratio is equal to C divided by 2 square root km. The mass of the car is fixed. The spring of the coil of the suspension is fixed. Engineer should design the damping coefficient so that the damping ratio become 1. But what should be the mass that we use in our calculation? It's gonna be the lump weight, lump mass of the vehicle. But after we have the passenger and the baggage on the car, the mass will change. So we cannot get the critically damped anymore. Yeah, in the exercise, we're gonna ask you what's gonna happen if we decide the C so that we can get the critically damped for the lump mass of the car. But after that, we have passenger and we have the baggage and the mass increase. How change to the damping ratio? Yeah, if the mass increase, you can see that if you select the C so that this become 1. If the mass increase and C and K still be the same, damping ratio will less than 1. And it will change to the case of the underdamped free vibration and has vibration. Yeah. So should we have a break? How do you think? Okay, we're gonna have 10-minute break and we will continue at 2:38. Okay, if you have any question, just ask me question.